I'm Norman Wildberger. Today we're going to look at the nullity and the rank of a linear transformation. We've talked last time about the kernel of a linear transformation and the image of a linear transformation in rather special cases when we're talking about transformations of two-dimensional space or three-dimensional space. Today we want to move up a level to talk about higher dimensional spaces, moving towards a general setup where we have a linear transformation from an n-dimensional space to an m-dimensional space. So the way we get such a thing is by a matrix. If we have an m by n matrix, let's say A, then that defines a linear transformation from n-dimensional space to m-dimensional space by this basic formula. So the linear transformation's name is T. V is a vector in Vn, in n-dimensional space, which we can think of concretely as a column vector with n elements. And what does that linear transformation do to that vector V? Well, it multiplies it by the matrix A on the left. So if A is an m by n matrix, and V is a column vector, or an n by 1 matrix, then this product is going to be an m vector, a vector with m components. So we're inputting a vector with n components, outputting a vector with m components by multiplying by this m by n matrix. That's the general setup for a general linear transformation that includes all kinds of special cases underneath it. We want to understand a general linear transformation like this. Now that's a big step up from what we're doing because we have to talk about n-dimensional space and m-dimensional space. We want to try to understand how we're going to visualize such a possibly complicated thing. Now by focusing on the kernel and the image of the linear transformation, we can gain a lot of insight into its geometric structure. And that's what we're going to be talking about today. And to make things a little bit simpler for us, we're going to look at things in a very special case. Okay? We're going to look at this particular relatively simple example, where our matrix A is a 3 by 4 matrix with 3 rows and 4 columns. And then if we multiply that by a vector with 4 components, we output a vector with 3 components. So we're talking about a linear transformation from 4-dimensional space to 3-dimensional space by multiplying by this matrix A. So one of the challenges in linear algebra is to be able to visualize things in higher dimension. And the key idea here is to make sure we understand very clearly what's happening in the lower dimensions, and to think of a pattern going from 1 dimension to 2 dimensions to 3 dimensions to 4 dimensions and higher. Now, so let me remind you, one-dimensional vector space. So one-dimensional space is just a line, and we can give coordinates to a line. Rather arbitrarily, we can assign a central point, an origin 0, and we can lay out equally spaced points giving coordinate system on that line. Now there's something to be said here about a distinction that we're making now that we didn't do before. Up till now we've been talking about affine space. And now I'm sort of shifting gears a little bit by talking about vector space instead of an affine space. So instead of talking about the affine space A, or A1, I'm now talking about the vector space V1. Let me remind you about the difference between points and vectors. If we're in a one-dimensional space, then any particular point, that's a point. While a vector is rather a pair of points, or a directed line segment. This, for example, represents the vector single component 3. And it represents the displacement between this point and this point. Maybe it's clearer if we look at the two-dimensional analog. Here's a two-dimensional plane with usual coordinates x and y. And I remind you that these axes don't have to be perpendicular, and generally they're not. And that although on any one axis the intervals are spaced equally, the separations along this line and along this line don't have to agree. So here they're a little bit wider than they are here. Okay, so this vector from this point to this point has coordinates 2, 1, and it's represented by a column vector with entries 2, 1. So this notation really represents the vector. Not so much a point, but rather a displacement or a pair of points. So there's a possibility for confusion here because the affine two-dimensional space and the vector two-dimensional space are almost the same thing. They are very close, but there's a subtle and important difference between them. The affine space consists of just points. The vector space consists of pairs of points or directed line segments. But it comes to the same thing because a vector like 2, 1 can actually be represented, once we've got coordinates, by that point there. That point, or the tip of the head of the vector, represents the vector. So effectively, there's not that much difference between an affine space and a vector space. But in practice, vectors can be added and scalar multiplied where points can't be. So linear transformations, it's better to think about them acting actually on vectors rather than on points. But sometimes we like to blur the distinction. So today I just want to make it explicit that we're really talking about vectors. We're really thinking about our linear transformation as acting on vectors. What about three-dimensional space? Well, here I remind you is our standard picture for that. We have three axes, the x-axis in this direction, the y-axis in this direction, and the z-axis in this direction. And if you're looking at it, the picture you should have in mind is that the y-axis and the z-axis are both in the plane of the board. Okay? While this x-axis, you should think of that as coming up towards you. So y is actually there, z is there, and the x-axis is actually coming out like this. And we're representing that picture on the two-dimensional plane, which necessarily involves a little bit of distortion or ambiguity, because the two-dimensional picture doesn't fully reflect the three-dimensional situation. But I've shown you before how to properly represent a vector in this situation. So for example, the vector 1, 3, 2 means 1 in the x direction, 3 in the y direction, and 2 in the z direction. And we can visualize that very concretely and accurately on our picture by drawing a box. A box with side 1 in the x direction, with side length 3 in the y direction, and side length 2 in the z direction. And so 1 in the x direction, 3 in the y direction, and 2 in the z direction ends up being the vector from here to here. So there's the vector 1, 3, 2. And I'm just reminding you here that the vector is actually an ordered pair of points in an affine space. And that, strictly speaking, if we translate the vector, it's really the same vector. So this vector AB is the same as the vector CD because they're parallel and they have the same displacement. Alright, so having understood one-dimensional, two-dimensional, and three-dimensional space, we're now ready to make the jump to try to visualize and understand four-dimensional space. So what is four-dimensional space? The easiest answer is purely algebraic. We're just working with vectors with four components, say x, y, z, and w. No geometry needs to be involved. We can define the basic operations of vector addition and scalar multiplication purely algebraically in terms of components. In the same way that we add vectors in two- or three-dimensional space or form linear combinations. So for example, if here's the vector v and here's vector u, both four-dimensional vectors, Then the sum is just obtained component-wise. So 1 plus 2 is 3, 3 plus 0 is 3, 2 plus minus 1 is 1, and minus 4 plus 5 is 1. So there's the sum of the two vectors. Here's a scalar multiple. 2 times this vector, just multiply each component by 2. If we want to take the difference, say u minus v, then we would get 2 minus 1 minus 3, 9. And we can take other combinations. We can take 4 times this vector minus 3 times that vector. We just do everything component-wise. That's a relatively simple, very down-to-earth, concrete way of thinking about what four-dimensional space is, purely algebraically, without any geometrical intuition or insight. But we do also want to have a rough geometric picture to augment our algebraic understanding. So geometrically, how do we think? Well, we've got 4 dimensions. We should roughly have 4 axes pointing in different directions. But these axes are not in 3-dimensional space, but in some other 4-dimensional space, which is not physically available to us to demonstrate in, because we live in a 3-dimensional world. However, we can represent or draw our 4-dimensional picture on a 2-dimensional piece of paper. Just like we draw our 3-dimensional world represented on the 2-dimensional piece of paper. So how would that go? Well, let's think about having 4 axes. So there's the x-axis, the first one, the y-axis, the z-axis, those 3 axes just the same as in 3-dimensional space. And now a new axis, the w-axis. Now the actual directions in which we're representing these axes is not that important. We could change this w-axis to be over here. In fact, we could choose any direction we wanted to. And we label each of the axes with some coordinates. So the x-axis, 1, 2, 3, etc. The y-axis, 1, 2, 3, 4, etc. The z-axis, say 1, 2, etc. And the w-axis, the new one, 1, 2, 3. And also negatives in the other directions. Now we have 4 basis vectors. E1, E2, E3, E4. E1, the unit vector in the x direction. E2, the unit vector in the y direction. E3, the unit vector in the z direction. And E4, the unit vector in this new w direction. Okay, so how are we going to represent or picture a general vector in this framework? Let's say the vector v consisting of the components 1, 3, 2, and minus 2. Well, so what this really means is it means 1 times E1 plus 3 times E2 plus 2 times E3 plus minus 2 times E4. So we're adding different components in different directions. We're adding 1 times the vector E1, 3 vector E2, 2 times the vector E3 up here, and minus 2 times the vector E4, which is where? Now that's E4, then that's minus E4, and that's minus 2E4. So how would we put all of that together? Well, we form the 4-dimensional analog of a parallelepiped. So let's start by just considering the 3-dimensional vector 1, 3, 2. And I remind you what we would do to visualize that. So let's ignore the w direction for a moment. And just think about 1 in this direction, 3 in this direction, and 2 in this direction. Then in black here I've shown you a parallelepiped, a box in ordinary 3-dimensional space with sides 1 in the x direction, 3 in the y direction, and 2 in the z direction. And then this point right here would be the result of going 1 step in the x direction, 3 steps in the y direction, and 2 steps in the z direction. So if we were just in 3-dimensional space, the vector 1, 3, 2 would be from here to here. Now we have to modify that by adding minus 2 times the vector E4. So we have to go from here and we have to add minus 2 times E4, which is to say we've got to go in this direction that amount. And I've represented that by here. So there's the resulting vector v. It's the combination of going in these 4 directions by these 4 amounts. And then what I've done, in fact, is shown you a 4-dimensional parallelepiped, or at least a 2-dimensional representation of it, obtained by taking this black parallelepiped in 3-dimensional space and having another copy of it right up here. I hope you can see that green box there. It's just a copy of the black box shifted up by this vector here. So this more complicated thing is a 2-dimensional representation of a 4-dimensional box. Okay. The 4-dimensional box has this 3-dimensional box as one of its faces. And you might like to see if you can find some other 3-dimensional faces. For example, the box there is another 3-dimensional face. All right, it's a little bit complicated, but in practice, actually drawing this vector accurately is not at all hard. Just have to remember that we go 1 in this E1 direction, 3 in the E2 direction, 2 in the E3 direction, and -2 in the E4 direction. So you don't even have to draw all of those boxes. You can just do one step at a time, adding the different vectors and their different components, and the result is to get up here. So that's the vector v represented geometrically. And there's our picture of 4-dimensional space. So with that preliminary, let's now go back to that linear transformation that we were looking at, and now try to understand it geometrically. So I remind you, we were talking about a linear transformation from 4-dimensional space to 3-dimensional space. Here's the formula for it. The formula is we take the vector v and we multiply it on the left by the matrix A. And here's the matrix A that we've been talking about. So let's write this down very explicitly. What exactly does this mean? So here's the linear transformation T, and now here we're applying it to a general vector in 4-dimensional space with components x, y, z, and w. What does the transformation do concretely? It takes the vector and multiplies it on the left by this matrix A. And what is that? Well, it's got a vector of 3 components. The first component is x plus 0y plus 4z minus 2w. The next entry is x minus y plus 3z plus 0w. And the last entry is x plus y plus 5z minus 4w. So here's another way of thinking about what the transformation does. It takes a 4-dimensional vector, this one right here, and sends it to this particular 3-dimensional vector. And what makes this a linear transformation is that the dependence here on the x, y, z, w, dependence here is linear everywhere. There are no x squareds, there's no sine of z's, there's no e to the y's. We're just taking linear combinations of the variables here. The simplest possible transformation, pretty well, that we can think of. That's the linear transformation that we're talking about. And we want to visualize that. We want to think of that as a transformation from 4-dimensional space to 3-dimensional space. So here's 4-dimensional space, like we've been talking about. Axes x, y, z, and some other w. This is really only a 2-dimensional representation of 4-dimensional space, but okay. And here's 3-dimensional space with directions x, y, and z as usual. That's also only a 2-dimensional representation of 3-dimensional space. Now, when we look at this linear transformation, this particular one, how are we going to understand this? We're going to ask 2 fundamental questions. Okay. The 2 fundamental questions are, first of all, which vectors over here get sent to the 0 vector? That turns out to be a very important, reasonably natural and crucial question. Okay? So which of the vectors in the initial space gets sent to the 0 vector? Certainly the 0 vector always gets sent to the 0 vector, because a linear transformation always sends 0 to 0. But there very well might be other vectors that get sent to 0. And I'm going to represent that space of vectors that get sent to 0 by this plane here. Now at this point we don't know if that's accurate or not. We don't really know what the set of vectors looks like, but it will turn out that it will be a plane. It will be a plane through the origin. And I've represented here by this, this sort of picture here, this rectangle, but it's actually, you should think of this as sort of a two-dimensional plane that goes through the origin, and it goes indefinitely in different directions. But it's all just two-dimensional. And that space is called the kernel of the linear transformation. KER stands for kernel. That's half of what we're going to need to understand the linear transformation. And the other thing that we'll need is a certain space over here in the three-dimensional space, the image of the transformation. What is that? Well, as the name suggests, it's just all those vectors over here that are actually the result of applying the linear transformation to some vector over here. So if we look at all the vectors over here, the linear transformation sends them to various vectors over here. But maybe the vectors that we get over here are not the whole space, but just some portion of it. We'll see shortly that that's in fact what happens. And the vectors over here that are in the image actually form a plane as well. It's now a plane in the three-dimensional space, and that plane we represent with this little rectangle, also going in different directions, and that's the image of the transformation. So these two spaces are fundamental in understanding the linear transformation. The kernel and the image. And I might as well tell you now what the nullity and the rank of the linear transformation are. The nullity is the dimension of this space, which is 2 because it's going to turn out to be a plane. And the rank is the dimension of this space, which also turns out, in this case, to be 2, because it's also a plane. But if I change the numbers, even just a little bit, I could very well get quite different pictures here. So exactly what the kernel and the image look like, and exactly what their dimensions are, depends very much on analyzing this particular transformation that we're looking at. All right, so let's introduce some official terminology to capture what I was just saying on the previous slide. We're going to just work with our particular linear transformation from V4 to V3. So what is this kernel of T? What is the actual definition? Well, we'll say that a vector V belonging to V4, the initial space, is a kernel vector for T precisely when T of V equals 0. In other words, when V is sent to the 0 vector by the linear transformation. And in this case, we write V belongs to kernel of T. And we say that V has the kernel property for T. V has the kernel property for T. All right, so a natural question is, okay, how can we find or describe all those vectors V in our initial space which have the kernel property for T? So the answer is we row reduce. We're really interested in the equation A times V equals 0. So we want to row reduce this matrix A. We can ignore the 0 on the right hand side. We don't have to put that into the augmented matrix because it's always going to stay 0. There's our matrix A. We're going to row reduce, use the first entry there as a pivot entry or a leading entry to get rid of the ones below it. So we take this row and we subtract row 1, and we take row 3 and we subtract row 1, and we get these two. And from here we might multiply this second row by -1 to make that a 1. And then we can take this third row and subtract that new second row. It'll just become 0, because this row here is just negative of that row. So after we do that, we get this already fully reduced row echelon form matrix. There are the leading entries. They're both ones. They're staggered down to the right, and everything in their columns is 0. How do we read off a solution from this? Well, we set the two non-leading variables to parameters. So the third and the fourth columns are assigned parameters. So let's say z equals lambda and w equals mu. And then using that, we solve for x in terms of the parameters lambda and mu. So the first equation would read x plus 0y plus 4z minus 2w equals 0. And if z is equal to lambda and w equals mu, then we can rewrite that as x equals minus 4 lambda plus 2 mu. And the second equation would give us y equals minus lambda plus 2 mu. So in terms of the two parameters, there's a description of the solutions. We could put it together in a sort of vector form by writing the vector v as x, y, z, w, and just taking this form and writing it as lambda times minus 4 minus 1, 1, 0, plus mu times the vector 2, 2, 0, 1. Now this is very nice. It's showing us that any vector v that satisfies a times v equals 0 is a linear combination of these two particular vectors. So in our picture of our four-dimensional space with axes x, y, z, and w, we have the vector minus 4, minus 1, 1, 0, which is where? Minus 4 in the x direction, minus 1 in the y direction, 1 in the z direction, and 0 in the w direction. So that's the vector v1, that one there. And the vector 2, 2, 0, 1, it would be represented by going 2 in the first direction, 2 in the y direction, 0 in the z direction, and then 1 in the w direction. That's down there. So that vector there, that's the vector v2. And now what this is telling us is that the kernel of t is just all possible linear combinations of those two vectors. And geometrically, we're just talking about the span of these two vectors in this four-dimensional space, so it really is a plane. Its dimension really is 2 because we found the two basis vectors right here corresponding to these two non-pivot columns where the parameters came from. So the nullity of the transformation, which is the dimension of this kernel, is 2 because there are two basis vectors. Alright, so let's go back to our linear transformation now. T from four-dimensional space to three-dimensional space. We now understand the kernel of T, which is a space inside V4. Now we're after a description of the image of T, which will be some collection of vectors inside V3. Here's the official definition. A vector W belonging to V3, belonging to this final space, is an image vector for T precisely when W equals T of V for some V in four-dimensional space. It's a little bit more complicated than the kernel definition, so you have to study this definition rather carefully. It's saying that a vector in here, let's call it W, is an image vector for T precisely when there is some vector V in here which is sent to W by the transformation T. So if we pick some random vector W in V3, maybe there's a vector that's sent to it, or maybe not. If there is, we write W belongs to the image of T. And we say that W has the image property for T. And the natural question now is, how can we find or describe those vectors W in V3 which have this image property for T? Okay, so how are we going to find or describe this space image of T? There's a linear transformation, T of V equals A times V. There's a matrix A. There's a vector V in 4-dimensional space. There's an output vector W in 3-dimensional space. We're interested in finding those 3-dimensional vectors which are actually the result of applying A to some vector in 4-dimensional space. So to get some initial sense of that, let's have a look at some particular vectors which do have this image property. We're going to do that by finding the simplest such vectors, by taking the matrix A and multiplying it by the simplest possible vectors in 4-dimensional space, which are the vectors with all zeros except for just a single one. So what happens if we take the matrix A and we multiply it by this first basis vector with components 1, 0, 0, 0? Well, if we multiply this matrix by the vector 1, 0, 0, 0, then we're going to get 1 times this and 0 all of those, 1 times this, 0 all of those, 1 times this, plus zeros of all of those. We're just going to get the vector 1, 1, 1. And what happens if we take the matrix A, we multiply by the basis vector 0, 1, 0, 0, sometimes called E2? Well, just take this matrix, think what happens if you multiply by the vector 0, 1, 0, 0. Then you're getting 0 plus 1 times this, plus zeros. 0 plus 1 times this, and zeros. Zeros and 1 times this, and zeros. So you're just picking up the second column. Similarly, if we multiply by the third basis vector, then we pick up the third column. And if we multiply by the fourth basis vector, we get the fourth column. So we see that the columns of the matrix A, they do have the image property. They're examples of vectors which are in the image of T. Because each one of these vectors, say this one, is actually A times some vector in V4. So at least the columns of A have the image property. So how do we describe all of the vectors that have this image property? So this is also a row reduction question, but it's a little bit more subtle than the kernel property question. We're interested in a vector W with components R, S, and T, let's say. We'll use R, S, and T to not get confused with X, Y, Z, and W coordinates in our 4-dimensional space. We actually have two different spaces here, 4-dimensional space and a 3-dimensional space. So by introducing R, S, and T, maybe there's less confusion. Okay, what are we interested in? We're interested in whether this augmented matrix has a solution. In other words, whether we can find numbers X, Y, Z, and W such that this matrix times X, Y, Z, W equals R, S, T. How do we figure that out? We row reduce this matrix. Now that's a lot like what we did just before, except that now on the right-hand side, instead of having zeros, we actually have some letters, R, S, and T, which are representing arbitrary numbers. All right, so what's our plan? We take this first row and we subtract it from rows 2 and 3. So row 2 minus row 1 gives us 0, minus 1 minus 0, 0. 3 minus 4 is minus 1. 0 minus 2 is 2. And S minus R is just S minus R. Third row, we take row 3, and so we subtract row 1. 1 minus 1 is 0. 1 minus 0 is 1. 5 minus 4 is 1. Minus 4 minus minus 2 is minus 2. And T minus R is T minus R. Okay, now we do the same thing as we did previously. We're going to multiply this row by minus 1 to make it look like this. So the s minus r becomes r minus s. And then we're going to take, well, we could just say here we could just add these two rows right here. It'd be simplest. Adding these two gives us zeros along here. And t minus r plus s minus r is t plus s minus 2r. It's now ready to read off whether we have a solution or not. We have our leading entries staggered here, and we have this last row with this entry here which we don't know what it is. It's in terms of our unknown numbers t, s, and r. But we can say that a solution exists precisely when this number is 0. If this number is 0, and that's a row of zeros, which doesn't matter, and then the two leading columns are these ones here. The two leading columns are on the left-hand side. There's always at least one solution. In fact, there will be 2 parameters worth of solutions. However, if this number is not 0, then that means that's actually another leading entry, and that means that last column is a leading column, which means there's no possible solution. Which we can just see immediately anyway, because this last row would be the equation 0 plus 0 plus 0 plus 0 equals something non-zero. So a solution exists precisely when t plus s minus 2r equals 0. Well, what is that? That's the equation of a plane in RST space, which is replacing x, y, and z now. This is a plane through the origin in RST space, and here's its equation. One equation representing a plane through the origin, because the right-hand side is 0, and that represents the image of the transformation. In other words, RST has the image property precisely when it lies on this plane. It's very important to understand this image property. So now I'm going to give you another way of thinking about what it means. So here's another approach. Let's have another look at our matrix A and a general vector in 4-dimensional space. What happens when we multiply A by this vector x, y, z, w? Well, I hope you all know that when you multiply a matrix on the right by a column vector, what you're getting is a linear combination of the columns of the matrix. Here's the first column, the second column, the third column, the fourth column. When you multiply by this vector, you're getting x times the first column, plus y times the second column, plus z times the third column, plus w times the fourth column. So, a vector in 3-dimensional space has the image property for t precisely when it's a linear combination of the columns of A. That's what this is. This is just a linear combination of the columns of the matrix A. So if W is a linear combination of the columns of A, then it has the image property. If it's not a linear combination of the columns of A, then it does not have the image property. So we can say that this is exactly the same as saying that W belongs to the column space of A. The column space of A is just the space spanned by the columns of A. In other words, all possible linear combinations of the columns of A. Now when we did the row reduction on the previous slide, at the end of the row reduction we would have the first and second columns being leading columns. That tells us that the column space of A has a basis consisting of the first 2 columns. This column and this column. That's a result of row reduction. So we don't need all 4 columns for the column space of A. The first 2 columns already span the column space. In other words, anything that you can get by adding multiples of these 4 columns, you can also get just by adding multiples of these first 2 leading columns. That's another consequence of the row reduction that we did on the matrix. So the column, we say the column space has the basis of these two vectors. So these two vectors are really the basis for the image of the linear transformation. All right, so this is a very important point, that the image of the transformation is just the same as the column space of the matrix. In other words, the space spanned by the columns of the matrix. And that you can compute a basis for that by row reducing and taking the corresponding leading columns. This column, this first column, this second column, because those are the columns corresponding to the leading columns after we've row reduced. We can put all this information together in a nice picture now. Our linear transformation T from 4-dimensional space to 3-dimensional space, given by multiplication by this matrix, does the following. Here's 4-dimensional space, here's 3-dimensional space. The linear transformation takes an arbitrary vector over here to some vector over here. And what we now know is that the kernel of the transformation, the vectors over here that have the kernel property, namely that when you look what happens to them, they end up being killed or going to the zero vector. Those vectors with the kernel property form a 2-dimensional space over here. Just all the linear combinations of these two particular vectors. The vector v1 minus 4 minus 1 1 0 and the vector v2 2 2 0 1. And these are actually reasonably accurate depictions of these two vectors in this 2-dimensional picture of 4-dimensional space. And over here, the interesting subspace is the image of the transformation. That's just what happens when you look at all the vectors here and see what happens to the whole space. All the vectors over here, you don't end up getting everything here, you just end up getting a plane. So this whole 4-dimensional space is sort of being collapsed onto a plane over here. And which plane? We can say very precisely, it's the plane spanned by these two vectors. That's the image of the transformation. And now associated to these two spaces inside our initial and final spaces are two numbers. The nullity of the transformation is the dimension of the kernel. The dimension of the kernel of T. What's the dimension? Well, the dimension is the number of elements in a basis. The number of vectors you need to span the space linearly independently. Okay, in this case, these two vectors here span the space and they're linearly independent. The dimension is 2 because it's a 2-dimensional plane. And the rank of the linear transformation is by definition the dimension of the image space. That's also a plane. It's also the span of two vectors. So the rank of the transformation is also 2. And we don't really know what these numbers are until we've row reduced the matrix for the linear transformation. To see what the interesting connection between these two numbers is, let's make two important observations about the process that we used in row reduction. So the first is that the basis vectors minus 4, minus 1, 1, 0 and 2, 2, 0, 1 of the kernel of T, these vectors corresponded to the non-leading or non-pivot columns of the row reduced matrix. Remember, we were solving the equation A times V equals 0. And we row reduced, and we saw that the third and fourth columns were non-leading columns, so they had to be assigned parameters. And there was one of these vectors for each of the parameters. That one went to the parameter lambda, and that was associated to the parameter mu. So the number of vectors here in the kernel of T corresponds to the number of parameters or the number of non-leading or non-pivot columns in the row reduced matrix. And the other sort of complementary observation is that the basis vectors of the image of the transformation, these vectors 1, 1, 1 and 0, minus 1, 1, they were in fact the first two columns of our initial matrix A. And they corresponded to the leading or the pivot columns of the row reduced matrix. The reason why we took those first two columns of the matrix A and not some other ones or some other number is because in the row-reduced form of A, it was the first two columns that were the pivot or leading columns. So the basis vectors for the kernel of T corresponded to the non-leading or non-pivot columns of the row-reduced matrix, while the basis vectors for the image of the transformation corresponded to the leading or pivot columns of the row-reduced matrix. I'll just remind you what the definition of nullity and rank are. The nullity is the dimension of the kernel, and the rank is the dimension of the image. So with this information, I hope you can guess what the relationship between these two numbers is. Let's have a look. Alright, so what is the relationship between the rank and the nullity of a linear transformation? Well, for the transformation we've been looking at, going from four-dimensional space to three-dimensional space, the proposition is that the nullity plus the rank equals 4. 4 being the dimension of the space that we're starting with. And the reason is almost obvious from the two observations we made on the last slide. Because the nullity of T is the number of non-leading columns once we've row reduced. And the rank is the number of leading columns once we've row reduced. So if we add them together, we just get the number of columns altogether. And if we're starting with a linear transformation from four-dimensional space to three-dimensional space, the matrix for it is a 3 by 4. It has 4 columns. The number of columns equals the number or the dimension of the space we're starting with. That's the reason why the nullity of T plus the rank of T equals the number of columns of the matrix we're starting with, which in this case is 4. And we can see that the argument is completely general. It doesn't depend on the fact that we looked at a particular transformation from four-dimensional space to three-dimensional space. The argument is very general, and here is the general theorem, which we call the Rank-Nullity theorem. If we have T, a linear transformation from n-dimensional space to m-dimensional space, then the rank of T plus the nullity of T equals n, the dimension of the space we're starting with. And the way you might want to think about this theorem is we're starting off with a certain number of dimensions, and when we transform them, some of them are lost. The ones that are lost are the ones in the kernel. They contribute to the nullity. And the ones that are left over, that end up actually being in the image, is the dimension of the image. So this is the number of dimensions we start with in our original space. This is the number that we end up losing, and this is the number that we end up with. It's another way of remembering reasonably easily this important theorem. Let's consider a transformation now from three-dimensional space to four-dimensional space given by this formula. It's another way of presenting a linear transformation. We're starting off with a vector with 3 components. We end up with a vector with 4 components. And the dependence on the output, on the input, is completely linear. That's a linear transformation. And our aim is to try to find the nullity and the rank. And let's check whether the rank-nullity theorem really works. Our first job is to rewrite it in matrix form. So we cook up the matrix that represents the linear transformation, and that's simply looking at these various coefficients that appear row on row and writing down this 4 by 3 matrix, let's call it A. Now what is the nullity of T? Well, it's the dimension of the kernel. And the kernel is a property of vectors in our initial space. So a vector v in our initial space has the kernel property when it's sent to 0. In other words, when you multiply it by this matrix A on the left, you get 0 output. And the rank of T, it's the dimension of the image. What's the image? Well, that's a property of vectors in the final space. So it's those W's in the final space that have the property that A times V equals W for some V in the initial space. All right, so to find or describe these two spaces, we need to row reduce this matrix. So how does the row reduction go? Well, we'll use this as the first leading entry or pivot entry to get rid of the things below it. So second row minus first row, third row minus first row, in other words third row plus the first row, and fourth row minus 2 times the first row, and we end up with this. It's almost already there. The second column doesn't contribute because the leading entry starts here and then the next leading entry is this one. Okay, it maybe be nicer to have a 1 there, so we're just going to swap these two rows here to bring a 1 in that place there. Then we're going to use this entry to get rid of everything below it. Well, that's immediate. We're just going to get 2 rows of zeros, and then this is the row echelon, fully reduced in fact, form of the matrix. Okay, so we can read off what the kernel looks like. The kernel consists of those vectors such that A times V equals 0. So in an augmented matrix form, that would have an extra row of zeros here on the right-hand side. Well, of the 3 columns, these 2 outside ones, the first and the third, are leading columns. This middle one is a non-leading column because it doesn't have a leading entry. So we assign a parameter to the non-leading variable. Y is set equal to lambda. And then we look at these equations. So this one reads x plus 3y equals 0. And so x would be equal to minus 3y, or minus 3 lambda, if y is lambda. And this one just would read z equals 0. No lambda involved there. And so the solution is the vector v is x, y, z. And in terms of lambda, it's lambda times minus 3, 1, 0. That's telling us that all solutions to this equation are multiples of the vector minus 3, 1, 0. Or in other words, the kernel of t is just the span of this one vector. It's the line consisting of all multiples of that vector. Those are the vectors with the kernel property. And the nullity is the dimension of that space. And since it's a line, its dimension is 1, the nullity is 1. And what about the image property of this linear transformation? Well, in that case, we're looking at this equation. We're trying to find out which vectors w have the property that they're equal to a times v for some v. And here's the matrix A that we started with. Here's that row reduction that we just did. And I remind you that the crucial fact about row reduction is that it preserves relations between columns. So notice, for example, that this first column and this second column are actually easily related. The second column is just 3 times the first column. That's true over here for these 2 columns, and it's also true for these 2 columns. This second column here is also 3 times the first column. That's true for any relationship between columns here. It's maintained in row reduction. So over here things are much simpler. Over here we can see that these 2 columns span the column space. In other words, the 3 columns are just linear combinations of the first and the third column. The second column is redundant. It's just a multiple of the first one. It's really these 2 columns that form a basis. And so we can conclude the same thing is true for the original matrix A, that these 2 columns, the first and the third one in the matrix A, form a basis for the column space. Every column in A is a multiple or linear combination of these 2, the first and the third. Because it's true over here, it's also true over there. And so we conclude that the image of the transformation, which is the same as the column space of the matrix A, is just a span of the first and the third columns of A. And these 2 vectors are not multiples of each other. They're actually in different directions, so they're linearly independent. And so this really is a plane. It's a two-dimensional plane. Its dimension is 2, and so the rank of this linear transformation is indeed 2. So here is a summary of what we learned. The linear transformation was from 3-dimensional space to 4-dimensional space. Here's our picture of 3-dimensional space, x, y, z axes. Here's our picture of 4-dimensional space with x, y, z, and w axis. In the original space, there's this distinguished line, the kernel. The vectors lying on here have the kernel property, and the ones that aren't on that line don't have the kernel property. And all the vectors lying on this line are multiples of, say, this particular one here, -3, 1, 0, which we computed. And the nullity of t is just the dimension of this kernel, which is 1. So all of the vectors here under the transformation get sent to 0. Now over here, in our 4-dimensional space, we have two distinguished vectors. 1, 1, minus 1, 2, which was one of the columns, and 0, 2, 1, minus 5, which was the other column. And these two vectors, I've drawn them here. So for example, this is a 1, and then 1 in this direction, and then -1 in the z direction will be down a little bit, and then 2 in this direction will be down there. Or that's that vector there. And you can check that this vector here is the vector 0, 2, 1, and then -5. And the space spanned by these, or the plane spanned by them, is a two-dimensional plane. Now in this picture, in this representation, it might look like this vector and this vector are almost multiples of each other. But that's a bit of an optical illusion, just because we're looking down on it this way. In fact, this vector might be in this direction, and this other one might be in this quite different direction here. When we look at them with this parallel projection, they almost look like they're in the same direction. But we can see that they're not multiples, and therefore their span really is a plane. And the rank is the dimension of that plane, which is 2. And what does the Rank-Nullity theorem say? It tells us that the rank plus the nullity is the dimension of the space we're starting with, 3 dimensions. And the way you can think about it is we're starting with 3 dimensions over here. We're collapsing one of the dimensions, so we only have 2 left over to get mapped onto the image over here. So it's a balancing out. The number that we start with equals the number that we're lost plus the number that we end up with. Okay, that's great. We've done a lot today. Some very important concepts, some very important computations, rank and nullity. And I hope you're seeing that the arguments that we're using here, the algebraic arguments, are really quite general. We could apply the same reasoning to bigger linear transformations if we wanted to. Let's have a look at some exercises now for you to practice. For our first exercise, we're looking at a transformation from 4-dimensional space to 3-dimensional space, given by this particular 3x4 matrix. And I'm asking you which vectors have the kernel property for this linear transformation. And there are 5 possibilities. Which of them have the kernel property, which of them don't? And our second exercise, still staying with this example, which vectors in this list have the image property for this linear transformation? Again, 5 different possibilities. Some of them do, and some of them don't. And our last exercise, I want you to describe the kernel and the image for each of these 4 different linear transformations. One of them from 4-dimensional space to 3-dimensional space by multiplying by that matrix. Another one also from 4 to 3, that matrix. One from 3-dimensional space to 4-dimensional space, multiplying by this matrix. And slightly different from 4-dimensional space to 2-dimensional space, given by multiplying by that matrix. So describe the kernel and the image, and I want you to verify for all of these the Rank-Nullity theorem. In other words, check that the Rank-Nullity theorem really does work. Okay, so we've done very well today. I hope you've learned a lot and are mastering rank nullity and thinking now more generally about linear transformations in perhaps higher dimensional space. It's really not all that hard and not all that different from 2 or 3 dimensional space. Now, the geometrical insights that we've been gaining are going to be put to use next time. We're going to go back to the standard problem of solving linear systems or inverting a linear change of coordinates. And we're going to look at it with fresh eyes with this now enlarged geometric intuition that we have. Thinking about rank, thinking about nullity, thinking about kernel, thinking about image. That's going to allow us to associate pictures to what formerly we just doing sort of mechanically and algebraically. And it's a powerful additional tool to make linear algebra simpler. We're going to visualize stuff next time. So next time it's geometry associated with systems of linear equations. I hope you'll join me for that. I'm Norman Wildberger, and thanks for listening.